This is a video from section 7.3, and it's on trigonometric substitution. And so in this section, what I want to do is I want to draw some triangles for you, because we're going to look at different substitutions. Now, let's go ahead and take a look at this first triangle. Now, suppose this is x, this is angle theta, and this is a. By the Pythagorean theorem, the hypotenuse should be the square root of x squared plus a squared. Now what we're going to do is we're going to look at the substitution. Now, I go by the triangle because it makes sense. So we want to define x in terms of theta. And so x over a, opposite over adjacent, is equal to tangent theta. If I multiply both sides by a, I get x equals a tangent theta. And we could even use the triangle further, because I want you to notice that the square root of x squared plus a squared divided by a, well, that's equal to secant theta. And so if I multiply both sides by a, I get square root of a squared plus x squared. Square root of x squared plus a squared is equal to a secant theta. So this is one scenario that can occur. Here's another scenario. Suppose I'm given a right triangle, and this angle is theta, and this side is x, this side is a, so the hypotenuse is a, and the base side is the square root of a squared minus x squared. Now, can x and the square root of a squared minus x squared be switched? Yes, you can definitely do that, and you will get a similar answer if you do. But in this scenario, I want to give you the substitution. Now, when you have the square root of a squared minus x squared, notice that a was the hypotenuse and x was the side opposite to angle theta. All right? Now, x divided by a is equal to sine of theta. So if I multiply both sides by a, I get x equals a sine theta. Okay? And furthermore, we can get a substitution for the square root of a squared minus x squared. Because remember, you're trying to transform everything in terms of thetas. So square root of a squared minus x squared divided by a is cosine theta. And if I multiply both sides by a, I get the square root of a squared minus x squared is equal to a cosine theta. And we're going to get one more in. So suppose I have a right triangle. Here's angle theta. And notice how a was the hypotenuse. Well, what if x was the hypotenuse and the side adjacent to angle theta is a, and the opposite side is the square root of x squared minus a squared? And so now let's go over the substitution. Now, again, I'm going to use trig. I'm going to say x divided by a is secant theta. And so that implies x is a secant theta. I'm reading literally right off the triangle. And the square root of x squared minus a squared divided by a, that's equal to tangent theta. And if I multiply both sides by a, I get the square root of x squared minus a squared is a tangent theta. Now, with that in mind, the directions say to evaluate the integral. And the main idea here is you want to transform this integral from x to something in terms of theta. So let's take a look at example 1. Suppose I had the integral of x squared divided by the square root of 9 minus x squared dx. So I'm going to draw a picture. Now, this is angle theta, okay? And so I'm looking at this denominator here. This is key, okay? Now, I want you to look back. So notice how it looks a little bit like number 2. Now, remember that 9 is equal to 3 squared. So this is going to be, well, let me say this. 3 is going to be the hypotenuse. The side opposite to angle theta is going to be x. And this base side is the square root of 9 minus x squared by the Pythagorean theorem. So let's go over our substitution. Remember that x over 3, let's erase this, by the way. X over 3 is equal to sine of theta. So I'm going right off the triangle. And so x is 3 sine theta. So, okay, great. I know what x is. And so dx, so we need to transform that dx. This is 3 cosine theta d theta. And we got one more thing to do, is we need to figure out what this expression is here. So, or let me say it another way. We need to figure out what the denominator is. So the square root of 9 minus x squared divided by 3 is cosine theta. So if I multiply both sides by 3, I get 3 cosine theta. And I'm in business because I want you to see what happens. So now, remember that x is 3 cosine, x is 3 sine theta. So I'm going to take 3 sine theta and I'm going to square it. I'm going to divide by 3 cosine theta and I'm going to multiply by 3 cosine theta d theta. But the 3 cosine thetas cancel, and if I square that, I get 9 sine squared theta d theta. But remember that sine squared theta is 1/2 of 1 minus cosine 2 theta. Okay? So I'm going to substitute that in. So I get 9 over 2 times 1 minus cosine 2 theta d theta. And so if you don't mind, I'm going to tell you what this integral is. You get 9/2 times theta minus 1/2 sine 2 theta plus c. So we're not quite done yet. Recall. I'll put the recall over here. Recall. Sine 2 theta is sine theta, is 2 sine theta cosine theta. So this is, I'm going to distribute the 9/2 in. So I get 9/2 theta minus 9 over 4 times 2 sine theta cosine theta, right, plus c. Now, let's go back to the triangle. Sine theta is x over 3. Cosine theta is square root of 9 minus x squared over 3. So let's write that down. This is x over 3 is sine theta. So, by the way, theta is arc sine of x over 3. So this is 9/2 arc sine of x over 3, like so, minus 9/2 times, by the way, the 2 canceled with 4, and you still have a 2 there. So we get 9/2 times x over 3 times, now cosine theta is square root of 9 minus x squared over 3. Plus c. And so this is 9/2 arc sine of x over 3 minus 1/2 x square root of 9 minus x squared plus c. And that is example 1. Example 2. Suppose I give you this one. Suppose I give you square root of 1 plus x squared divided by x dx. Now, when you see a sum of squares, so I always go back to the picture. Now, here's theta. Sums of squares, I'm thinking of legs. So the side opposite angle theta is x, the adjacent side is 1, and the hypotenuse, and notice how I'm going to get the square root of x squared plus 1. It's not a coincidence. When you have a sum of squares, you have 2 legs. Now, x over 1 is tangent theta. So dx is secant squared theta d theta. And the square root of x squared plus 1 over 1 is secant theta. So notice it's all substitution all the time. I want to transform everything in terms of x. I want to transform the integral from x to theta, the whole thing. And so this is the integral of secant theta divided by x, which is tangent theta, times dx, which is secant squared theta d theta. Now, this one's a little more interesting because what I'm going to do is I'm going to write this as secant theta divided by tangent theta, and then secant squared theta can be replaced with 1 plus tangent squared theta, and then you're integrating with respect to theta. And this is the integral of secant theta over tangent theta plus secant theta tangent theta d theta. So I'm going to carry this down a bit. Now, this is equal to the integral of cosecant theta plus secant theta tangent theta d theta. So I claim, if we're not sure, secant theta is 1 over cosine theta. Tangent theta is sine theta over cosine theta. But the cosine thetas cancel, And remember that 1 over sine theta ends up being cosecant theta. Okay? And so the integral is natural log. I claim the integral of cosecant theta d theta is natural log of cosecant theta minus cotangent theta. And this is in absolute values. All right? The integral of secant theta d theta is secant theta. And then we're going to add c. Now, if we go back to the triangle, cosecant theta is square root of x squared plus 1 divided by x. So we get the square root of x squared plus 1 divided by x minus cotangent theta is 1 over x plus, now let's go back, secant theta is 1 over, well, excuse me, secant theta is square root of x squared plus 1 plus c. And this is one of those you want to talk to your instructor about how far they want you to simplify. But I would be more apt to leave it like this. I would get a common denominator, and I would write this as the natural log of the square root of x squared plus 1 minus 1 over x plus the square root of x squared plus 1 plus c. I would write it like this because even if you broke apart the natural log, there's nothing that cancels. So I would find this an acceptable solution, but that is going to be instructor dependent. So it's just something you want to keep in mind. If we look at example 3, I want to point out this one. This one's a very interesting question. Now, could you do this by u substitution? Absolutely. But why? I could let u be x squared plus 1. du is 2x dx. And so x dx is 1/2 du. And that's acceptable. It never says you had to do it by trigonometric substitution. But if your instructor said, solve this integral by trigonometric substitution, you need to use trig functions, okay? And so here you get 1/2 the integral of 1 over the square root of u du, which is equal to 1 over 2 times the integral of u to the negative 1/2 du. And so this is 1/2 times u to the 1/2 divided by 1/2 plus c. But as you can see, the 1/2s should cancel, right? And so the answer here is the square root of x squared plus 1 plus c. And that is a totally acceptable way to do this type of question. Okay. Example 4. Now, in example 4, suppose we had something like this. Okay. Suppose we had the integral from 0 to 1 of 1 over x squared plus 1 to the second power dx. So I want you to draw a triangle. Here's angle theta. Here's x. Here's 1. Here's the square root of x squared plus 1. Same type of substitution. Now, x is equal to tangent theta. Because x over 1, right? But x over 1 is x. dx is secant squared theta d theta. And square root of x squared plus 1 is equal to secant theta. But to get an expression for x squared plus 1 to the second, we have to raise both sides to the fourth power. And so x squared plus 1 squared is equal to secant to the fourth theta. Now, my limits are in terms of x, but I want my limits in terms of theta. So when x is 0, I know that tangent of 0 is 0, so theta is 0. When x is 1, theta is pi over 4. So remember that tangent of pi over 4 is 1. So we never have to go back now in terms of x's. So we're done because it's a definite integral. So we have the integral from 0 to pi over 4 of. Now we get 1 over secant to the fourth theta times dx, which is secant squared theta d theta. And so this is the integral from 0 to pi over 4 of cosine squared theta d theta. And so this is the integral from 0 to pi over 4 of 1/2 of 1 plus cosine 2 theta d theta. So just step by step. And so this is equal to 1/2 of theta plus 1/2 sine 2 theta evaluated from 0 up to pi over 4. If I pop the pi over 4 in, I get 1/2 of pi over 4 plus 1/2 sine. Now, pi over 4 times 2 is pi over 2. And remember that sine of pi over 2 is equal to 1. And so this is pi over 8 plus 1/4. And we're done. And that was example 4. If we take a look at one more example, in example 5, suppose we had something like this. Suppose we had the integral of 1 over the square root of x squared plus 2x plus 5 dx. Now, you have to manipulate this a little bit. And so I want you to notice that I'm going to rewrite this as 1 over the square root of x squared plus 2x. Remember that 5 is equal to 1 plus 4. Now, why did I do that? Because x squared plus 2x plus 1 I know is a perfect square. It's no coincidence that I could take half of 2 and square it and get 1. And you're just thinking about what do you have to add to 1 to get me back up to 5? And I know that 1 plus 4 is 5. And so this is the integral of 1 over x plus 1 squared plus 4. And this is under the radical. And we're integrating with respect to x. Now, if we're comfortable, I'm going to label the triangle from here. So I'm going to make this side x plus 1 and this side 2. And the hypotenuse, the square root of x plus 1 squared plus 4. And here's my angle theta. And so x plus 1 is equal to 2 tangent theta. So dx is 2 secant squared theta d theta. And the square root of x plus 1 squared plus 4 is 2 secant theta. And then it's just straight substitution. And so this is equal to the integral of, now dx is 2 secant squared theta. And by the way, I'm integrating with respect to theta. Do not forget that. My denominator is 2 secant theta. It's all trigonometry. And so this is the integral of secant theta d theta. And so this is natural log of secant theta plus tangent theta plus c. But secant theta is square root of x plus 1 quantity squared plus 4, which, by the way, is just nothing more than that, okay? So we get square root of x plus 1 squared plus 4, and I'm going to divide by 2 plus x plus 1 over 2 plus c. Now, I can simplify this a little bit, and I'm going to show you. So I could write this as natural log of the square root of x squared plus 2x plus 5 plus x plus 1. Now, I'm going to subtract natural log of 2 and then add c. But that negative natural log of 2 can get absorbed into that c. And so the answer here is natural log of the square root of x squared plus 2x plus 5 plus x plus 1 plus k. And this is where k is equal to c minus natural log of 2. And that's going to conclude this video for section 7.3. And we worked on 5 examples of trigonometric substitution. Okay, thank you.